Right now, somewhere in the night sky, there are whole galaxies so faint that no telescope ever built can detect them. They are too small, too dim, and too far away. And there may be trillions of them. For decades, scientists told us the observable universe contained roughly 100 billion galaxies. Then one telescope stared at a seemingly blank patch of sky for 10 straight days, and that number exploded. The real count may be 2 trillion, possibly far more, and the unsettling truth is that most galaxies in the universe have never been observed by any human instrument. What we see in our deepest images may be just the bright surface of something vastly larger and almost entirely hidden. This is the story of what we are missing. If you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, get yourself nice and comfortable. Let's begin. How many galaxies exist in the universe? It sounds like a question that should have an answer. A specific number you could look up, memorize, and repeat at a dinner party. The kind of fact that belongs on a quiz show or printed in the opening paragraph of a textbook. Scientists have been trying to answer it for more than a century, and every single time they believed they had the number, the universe proved them wrong. Not by a small margin, not by some minor percentage, by factors of 10, by factors of 100. The count kept climbing decade after decade, and the reason it kept climbing reveals something deeply uncomfortable about how we observe reality. We are not merely counting galaxies out there in the darkness. We are measuring the limits of our own ability to see, and every time those limits have expanded, the universe has turned out to be fuller, denser, and more crowded than anyone predicted. To understand why this question is so deceptively hard, you have to go back to a time when the question itself did not even make sense. For most of recorded history, nobody imagined that other galaxies existed at all. The night sky was a dome of fixed stars, unchanging and eternal. The fuzzy smudges visible on very clear nights were called nebulae, from the Latin word for cloud, and that is precisely what astronomers assumed they were. Clouds of glowing gas drifting within our own star system. The Milky Way was not simply our galaxy. It was the universe. Everything that existed, every star and every wisp of luminous gas, belonged to one single system surrounded by infinite emptiness. There was nothing else, because there was nowhere else for anything to be. This assumption held for centuries. Galileo turned his telescope toward the Milky Way in 1610 and resolved the band of light into countless individual stars, proving that the glowing arc across the sky was made of suns too faint for the naked eye to separate. William Herschel attempted to map the shape of this star system in 1785 by counting stars in different directions. He concluded that the Milky Way was a flattened disk with the sun somewhere near its center. He was wrong about our position and wrong about the size, but his fundamental insight that we inhabited a disc-shaped collection of stars was correct. For the next century, astronomers refined Herschel's map, debated the size of the disk, and argued about what lay beyond it. Most concluded the answer was nothing, but the mystery deepened every time telescope technology improved. In 1845, an Irish nobleman named Lord Rosse built the largest telescope in the world, a 72-inch reflector so enormous it earned the nickname the Leviathan of Parsonstown. When Rosse pointed this instrument at certain nebulae, he saw something nobody had ever witnessed: spiral structure. Some of the fuzzy patches resolved into elegant pinwheel shapes, with luminous arms curling outward from a bright central core. These spiral nebulae looked nothing like simple gas clouds. They appeared organized, structured, systematic. They looked like rotating systems of immense scale. But Rosse could not determine whether they were modest structures within the Milky Way or colossal structures millions of light years beyond it. The telescopes of the 19th century could reveal the spirals but could not measure how far away they were. Without distances, the question of their true nature remained open, tantalizing, and unresolved. The philosopher Immanuel Kant had speculated as early as 1755 that some nebulae might be separate island universes, each one a vast collection of stars so distant it appeared as a faint smudge against the sky. Thomas Wright had proposed something similar a few years before Kant, but speculation is not evidence. and for more than 150 years after Kant's proposal, nobody could confirm whether the spiral nebulae were nearby gas clouds or distant galaxies comparable to our own Milky Way. The technology was not sufficient. The measurements were not precise enough. The question remained suspended in the air like an unanswered challenge, waiting for an instrument powerful enough to settle it. By the early 20th century, new observations had split astronomers into two warring camps. Vesto Slipher, at the Lowell Observatory, measured the velocities of spiral nebulae by studying the shifting wavelengths of their light. He found that many were moving at speeds far exceeding anything inside the Milky Way. Some receded at hundreds of miles per second. These extreme velocities suggested the spirals were very distant objects following their own independent trajectories. But other astronomers pointed to nova observations within the spirals that appeared too bright for extragalactic distances. The evidence was genuinely contradictory, and reasonable scientists could examine the same data and reach opposite conclusions. This conflict reached a dramatic peak in 1920, during what historians now call the Great Debate. Harlow Shapley stood before the National Academy of Sciences in Washington and argued that the Milky Way was enormous, perhaps 300,000 light-years across, big enough to contain the spiral nebulae within it, or just beyond its fringes. Heber Curtis argued the opposite. He contended the Milky Way was much smaller, roughly 30,000 light-years wide, and that the spiral nebulae were independent galaxies at immense distances. Both men were partially right and partially wrong about different aspects of the problem. Neither could deliver a decisive proof because the data was simply not good enough. The debate ended without a clear winner, and astronomy remained split on one of the most fundamental questions about the nature of the cosmos. Was the Milky Way everything, or was it merely one island among many in an ocean of space far vaster than anyone had imagined? Then Edwin Hubble settled the argument forever. Working at the Mount Wilson Observatory in the mountains above Los Angeles, Hubble had access to the 100-inch Hooker telescope, the most powerful astronomical instrument on Earth at that time. Its enormous mirror could gather light from objects far too faint for any smaller telescope to detect. Over the course of 1923 and 1924, Hubble used this giant eye to study the Andromeda Nebula in extraordinary detail. Night after night, he photographed the same region, comparing plates taken weeks apart, searching for stars that changed brightness. He found them. Embedded within the spiral arms of Andromeda, he identified individual Cepheid variable stars. This was the breakthrough that changed everything. Cepheid variables are stars that pulse. They brighten and dim in regular, predictable cycles that can last anywhere from a few days to several weeks. What makes them invaluable to astronomers is a relationship first established by Henrietta Swan Leavitt in 1912. Leavitt discovered that the period of a Cepheid's pulsation is directly linked to its true luminosity. A Cepheid that pulses slowly is intrinsically brighter than one that pulses quickly. This relationship turns every Cepheid into a cosmic distance marker. Measure how rapidly the star pulses to determine how luminous it truly is. Compare that true luminosity to how bright the star appears from Earth. The difference reveals the distance. The dimmer the star appears relative to its true output, the farther away it must be. The mathematics is straightforward. The implications were revolutionary. Hubble measured the pulsation periods of several Cepheids in Andromeda and calculated their distances. His result placed Andromeda roughly 900,000 light-years from Earth. Modern measurements have revised this figure to approximately 2.5 million light-years, but even Hubble's initial estimate was devastating to the single galaxy model. The Milky Way, even under Shapley's most generous size estimate, extended only about 300,000 light-years. Andromeda was 3 times farther away than the maximum size of our entire galaxy. It could not possibly be inside the Milky Way. It was not a cloud. It was not a nebula. It was an entirely separate galaxy, a distinct island of billions of stars with its own spiral arms, its own history, its own independent existence. The realization landed like an earthquake. If Andromeda was a separate galaxy, then the other spiral nebulae were almost certainly separate galaxies too. In one stroke, the known universe expanded from a single star system into a cosmos populated by countless galaxies, spread across distances so immense that light required millions of years to travel between them. The universe was not one city. It was an ocean filled with cities, each one a galaxy in its own right. each one separated from its neighbours by gulfs of nearly empty space. By 1929, Hubble had pushed the revolution even further. He demonstrated that distant galaxies were moving away from us, and that the farther away a galaxy was, the faster it receded. The universe was expanding. Space itself was stretching, carrying galaxies apart in every direction. This discovery overturned the ancient assumption of a static cosmos and led directly to the Big Bang theory. But the expanding universe did something else that would haunt every future attempt to count galaxies. It transformed the counting problem from a question about objects in space into a question about objects in space and time simultaneously. In a static universe, you could in principle photograph the entire cosmos at a single moment. Every galaxy exists at a fixed distance. You simply need a powerful enough telescope to see them all. In an expanding universe, that picture shatters. Distance and time become entangled. The farther away an object is, the longer its light has been travelling, which means the further back in time you are seeing. You are never observing the universe as it is. You are observing it as it was, layer by layer, with each increasing distance revealing a progressively older era. This entanglement means that the volume of countable space is not a simple sphere extending outward to infinity. It has a boundary. Light has a speed. The universe has an age. In the time since the cosmos began, light from objects beyond a certain distance has not had time to reach us. Those objects exist, but they are invisible, permanently beyond the reach of observation. The expanding universe created a horizon, a limit to what can be seen, and every galaxy count performed from this point forward would apply only to the volume within that horizon. This was a new kind of limitation, not a technological barrier that better instruments could overcome, but a physical boundary written into the structure of reality. Expansion also meant that the universe was denser in the past. Space was smaller, galaxies were closer together. Farther back in time, the cosmos was more crowded, more chaotic, more violent. Counting galaxies across this evolving landscape was fundamentally different from counting stationary objects in a fixed container. The population was changing while you tried to count it. The container was growing while you tried to measure it. And the boundary of what you could see was determined not by your telescope, but by the speed of light and the age of the universe. These complications were not immediately obvious in the decades following Hubble's discovery. Early efforts to count galaxies were crude by modern standards. Astronomers photographed regions of the sky using ground-based telescopes, identified galaxies by their fuzzy, extended appearance, and attempted to estimate the total population across the entire celestial sphere. The fundamental obstacle was always the same: sensitivity. Ground-based telescopes peer through Earth's atmosphere, which blurs images, scatters incoming light, absorbs certain wavelengths entirely, and generates a diffuse background glow that drowns out the faintest objects. Even the best observatories in the world, perched on dry mountaintops in Chile or Hawaii, faced a hard ceiling on what they could detect. Below a certain brightness, galaxies simply vanished into the atmospheric noise. Through the 1950s and 60s, as photographic surveys expanded and telescope mirrors grew larger, estimates of the total galaxy count settled into a rough consensus. Most astronomers cited numbers between 50 billion and 100 billion galaxies in the observable universe. These figures were acknowledged as incomplete. Everyone understood that fainter galaxies existed below the detection threshold, but nobody knew how many. The estimates carried large uncertainties and entered textbooks as approximate answers to a question that seemed, at the time, to be approaching a solution. It was not. The problem ran deeper than atmospheric interference. Counting galaxies from inside the universe is fundamentally different from counting objects on a table. You cannot step outside for a wider view. You cannot illuminate the dark corners. You are embedded within the thing you are trying to measure, surrounded in every direction by distances so staggering that light itself requires billions of years to cross them. And because light travels at a finite speed, looking deeper into space means looking further back in time. The galaxies you observe at extreme distances are not the galaxies that exist there now. They are the galaxies that existed billions of years ago, when their light first began its journey toward your telescope. You are never photographing the current universe. You are photographing a composite of its past, a layered time exposure where every increasing distance reveals an older era. Imagine trying to count every building in a massive city at night from a helicopter hovering above the downtown core. You can see the skyscrapers easily. Their illuminated windows blaze against the darkness. You can count the major towers, the tall apartment blocks, the brightly lit commercial centers, but the small houses with dim porch lights blend into the background. Single-story structures with no lights on at all are completely invisible from your altitude. You know the city contains far more buildings than just the glowing towers. You can see the faint collective glow they contribute to the horizon, but you cannot count them individually. Your tally depends entirely on how sensitive your instruments are and how dark the sky is around you. Change the camera, improve the sensor, fly lower, the count changes every time. This was the situation astronomers faced by the late 20th century. Every galaxy survey counted what it could detect and then extrapolated from there. But the extrapolation rested on assumptions about the population of faint galaxies that had never been tested by direct observation. Nobody knew if faint galaxies were moderately common or overwhelmingly abundant. The answer to how many galaxies existed depended on information that no existing instrument could provide. What science needed was a telescope free from Earth's atmosphere, capable of staring at a single patch of sky for days without interruption, accumulating light from objects so faint they had never registered on any detector. Science needed an eye above the sky. The Hubble Space Telescope launched in 1990 aboard the Space Shuttle Discovery. Its early years were a setback. A tiny manufacturing flaw in the primary mirror blurred every image the telescope produced, turning what should have been the sharpest astronomical instrument ever built into a source of frustration and embarrassment. In 1993, astronauts installed corrective optics during a servicing mission that ranks among the most dramatic repair jobs in the history of engineering. The fix worked. Hubble was transformed into the instrument it was always meant to be, capable of resolving objects 10 times fainter than any ground-based observatory, and holding its gaze with stability impossible beneath the turbulent atmosphere. The universe came into sharper focus than it had ever been seen before. Early, deep exposures with the repaired telescope immediately revealed something tantalizing. Wherever Hubble pointed, it found galaxies in staggering numbers, not just a handful per field. Hundreds, thousands. Many of these distant galaxies were tiny, irregular, and chaotic, nothing like the grand spirals and smooth ellipticals familiar from nearby space. They appeared to be galaxies in earlier stages of evolution, caught in the act of assembling themselves from smaller fragments. The deep universe was messy, crowded, and violent. These initial results hinted that a much deeper observation might reveal an entirely different picture of the cosmos than anyone expected. Robert Williams was the director of the Space Telescope Science Institute, the organization responsible for managing Hubble's scientific operations. As director, Williams had a discretionary allocation of observing time that he could assign at his own judgment. In 1995, he proposed using that time for an experiment that many senior colleagues considered reckless. He wanted to point Hubble at nothing. The target was a tiny patch of sky in the constellation Ursa Major, near the handle of the Big Dipper. Williams and his team selected it specifically because it appeared empty. The patch sat far from the bright, crowded plane of the Milky Way, far from known galaxy clusters, far from any prominent celestial objects. To ground-based telescopes, there was nothing there. No galaxies worth studying, no interesting stars, no obvious science. Just a dark gap in the sky no wider than a grain of sand held at arm's length. Williams proposed staring at this gap for 10 consecutive days during the Christmas holiday period of 1995. Hubble would take 342 separate exposures through 4 different wavelength filters, accumulating more than 100 hours of total exposure time on a target smaller than a dime viewed from 75 feet away. The patch covered roughly 5 square arc minutes of sky. Nearly 30 million identical patches would be needed to tile the entire celestial sphere. The criticism was immediate and vocal. Hubble observing time was the most fiercely competitive resource in all of astronomy. Hundreds of research teams submitted proposals every year, and most were rejected. Using 10 precious days of the most powerful telescope in existence to photograph a blank spot in the sky struck many astronomers as an indefensible waste. Williams understood the risk. He acknowledged later that if the experiment had failed, if the image had returned showing nothing of scientific value, the decision could have damaged his professional reputation. But he trusted that the darkness was concealing something important. He believed the emptiness was an illusion created by the limits of previous instruments. On December 18, 1995, Hubble began its long stare. For 10 days, the telescope gathered photons from that tiny hole in the sky, building an exposure so deep that objects 4 billion times fainter than what the human eye can see would emerge from the darkness. Orbit after orbit, the faint light accumulated on the camera. When the data was processed, calibrated, and combined into a single composite image, what emerged was one of the most important photographs in the history of human knowledge. The Hubble Deep Field contained roughly 3,000 objects in that minuscule patch of apparent emptiness. Almost every single one of them was a galaxy, not foreground stars within the Milky Way. Entire galaxies, each one a collection of millions or billions of stars, scattered across billions of light-years of space and time. Some were bright spirals at moderate distances, their arms clearly resolved, their structures recognizable. Others were small blue clumps, galaxies in the process of forming their first generations of stars. The faintest objects were tiny red smudges only a few pixels across, galaxies so distant that their light had been traveling for more than 10 billion years before it reached Hubble's detector. The image was a vertical core sample drilled through the full depth of cosmic history, revealing galaxies at every stage of evolution from the recent past to the first billion years after the Big Bang. The impact on astronomy was seismic. If that minuscule, deliberately chosen blank spot contained 3,000 galaxies, then the full sky must be saturated with them. Extrapolating the Hubble Deep Field galaxy density across the entire celestial sphere yielded an estimate of roughly 100 to 120 billion galaxies in the observable universe. This number was consistent with the upper range of previous estimates, but now rested on the strongest direct evidence ever collected. The galaxy count was no longer a rough guess, it was an observation. Williams had gambled on emptiness and discovered that the universe has no empty spaces. Everywhere you look, if you look deeply enough, galaxies fill the darkness. The image became iconic almost immediately. It appeared in newspapers, magazines, and television broadcasts around the world. Scientists who had privately questioned the decision to photograph nothing were now staring at 3,000 galaxies and recalibrating everything they thought they knew. The deep field did not just change a number, it changed the way astronomers understood the sky. Before the image, an empty patch of sky was empty. After it, every dark gap between the visible stars became a potential reservoir of galaxies, too faint for the eye or for any existing telescope to resolve. The universe's emptiness had been exposed as an illusion of sensitivity. The darkness was full. It had always been full. We simply lacked the instruments to see it. But the deep field revealed something even more important than the number. It exposed a fundamental problem with the number. The 3,000 galaxies in the image were the ones bright enough for Hubble to detect at that exposure depth. Right at the faintest edge of the image, galaxies appeared as barely perceptible smudges, teetering on the boundary between signal and noise. Just below that boundary, invisible by the narrowest possible margin, there had to be more. The question was how many more? And the answer to that question depended entirely on how the population of galaxies was distributed across the full range of sizes and brightnesses. Every piece of evidence suggested the unseen population was enormous. In our own cosmic neighborhood, small galaxies vastly outnumber large ones. The Milky Way is orbited by dozens of known dwarf galaxies, tiny satellites containing anywhere from a few 100,000 to a few billion stars each. Andromeda has its own swarm of dwarfs. New ultra-faint dwarf galaxies keep turning up in survey data, objects so dim they were overlooked for decades despite being cosmically nearby. If this pattern of many small galaxies for every large one held throughout the universe, then for every galaxy Hubble could see in the deep field, there might be dozens or hundreds more hiding below the detection floor. The counting problem was compounding in a way nobody had anticipated. It was no longer a matter of simply pointing a telescope and tallying what appeared. It had become a question about the full statistical population of galaxies across all sizes, all luminosities, all distances, and all cosmic eras, and then inferring how many of those fell below the threshold of observation. The Hubble Deep Field had cracked open this problem. It had not solved it. It had demonstrated that the answer to how many galaxies exist depended not on how many we could see, but on how many we could not see. The invisible majority was out there, hiding in plain darkness. And there was another complication that made the problem harder still. The universe is not frozen in time. It evolves. Galaxies in the distant past were fundamentally different from galaxies in the present. The deep field showed this directly. The most distant objects in the image were small, irregular, and chaotic. Galaxies in the early stages of assembly, many in the process of colliding with neighbors and merging into larger structures. This merging process means the total number of galaxies changes over cosmic time. Billions of years ago, galaxies were far more numerous because they had not yet combined. Over the ages, mergers reduced the total count while increasing the average size. Counting galaxies across cosmic history is like counting raindrops on a window, where the drops are constantly merging into larger drops. The total depends on when you look. To confirm that the deep field result was not an artifact of a single unusual direction, a second deep exposure targeted the southern sky in 1998. The Hubble Deep Field South revealed remarkably similar galaxy densities. The universe looked the same whether you pointed north or south. The galaxy count was not a local anomaly. It was a universal fact. The sky was uniformly dense with galaxies in every direction, and the 100 billion estimate appeared solid. But solid is not complete. 100 billion was the number of galaxies bright enough for Hubble to detect in its deepest exposures. The actual total, including every galaxy too faint, too small, too diffuse, or too distant for any existing instrument to register, remained unknown. And the gulf between the observed count and the true count was about to become the defining puzzle of 21st century cosmology. What came next required an even deeper plunge into the darkness. Scientists prepared to hold Hubble's gaze on a single patch of sky for not 10 days but 11, pushing the telescope to the absolute ceiling of its capability. They chose a seemingly empty region in the constellation Fornax, and they aimed to photograph galaxies that no human instrument had ever captured. Objects so dim they had been invisible since the first billion years of cosmic time. The image that emerged would not simply adjust the number. It would detonate the old count entirely and force astronomers to confront the possibility that most galaxies in the universe had never been seen at all. The patch of sky that scientists chose for the deepest observation Hubble had ever attempted sat in the constellation Fornax, a faint grouping of stars visible from the southern hemisphere. Like the original deep field target, this region was selected because it was boring. No bright stars contaminated the foreground. No known galaxy clusters dominated the view. No prominent nebulae cluttered the frame. It was a carefully chosen window of cosmic silence, a place where the telescope could stare without distraction at whatever lay in the farthest background of the universe. Between September of 2003 and January of 2004, Hubble pointed its upgraded advanced camera for surveys at this tiny rectangle of sky and held its gaze. The telescope accumulated 800 separate exposures over the course of 400 orbits around Earth, building up a total exposure time of 11 1/3 days. This was not merely longer than the original deep field observation. It was fundamentally deeper. The upgraded camera was far more sensitive than the instrument used in 1995. Each photon that arrived from the distant cosmos was captured with greater efficiency, meaning that the same amount of observing time reached fainter objects. The combination of longer exposure and better technology pushed the detection threshold to an entirely new level. Objects that had been invisible to the original deep field, galaxies lurking just below the noise floor, would now emerge from the darkness. When the data was processed and released to the world, the Hubble Ultra Deep Field became the deepest portrait of the cosmos ever created at optical and near-infrared wavelengths. Approximately 10,000 galaxies filled that small rectangle of sky. 10,000. In a patch of the heavens so tiny that it covered less than 1/13 millionth of the total sky, the image reached back in time to within a few 100 million years of the Big Bang itself. The most distant galaxies appeared as small red smudges, their light so severely stretched by the expansion of space that it had shifted from ultraviolet wavelengths into the near-infrared. These were galaxies as they existed when the universe was less than 1 billion years old, young structures beginning to assemble themselves from primordial gas in a cosmos that was still hot, dense, and chaotic. But what struck astronomers was not only the number, it was the staggering variety. The ultra-deep field was a gallery of galactic evolution displayed across billions of years in a single frame. In the foreground, relatively nearby galaxies appeared as fully developed spirals and ellipticals, their structures familiar and well-defined. Moving deeper into the image and further back in time, the galaxies changed. Spirals became less organized. Arms appeared fragmented, clumpy, asymmetric. Smooth ellipticals gave way to irregular blobs with no clear geometry at all. At the farthest distances, the galaxies barely looked like galaxies. They were compact knots of blue light, each one a furious burst of star formation crammed into a region smaller than one of the Milky Way's spiral arms. Some appeared to be in the process of colliding, their shapes distorted by gravitational interactions with neighbours only a few thousand light-years away. Others sat alone, tiny and fierce, burning through their gas supply at rates that could not be sustained for long. Each of these faint smudges was an entire galaxy, a gravitationally bound collection of millions or billions of stars, planets, gas clouds, and dark matter. The smallest red dot in the image, barely distinguishable from detector noise, was a system that might have contained the raw material for 100 million worlds, and it had been invisible to every telescope ever built until Hubble stared at this one spot for 11 days. The ultra-deep field did not just find more galaxies, it revealed the universe's past in a form that was simultaneously beautiful and humbling. Every pixel that contained a galaxy was a window into an era that had been completely inaccessible before. The ultra-deep field was not merely a prettier version of the original deep field. It revealed an entirely new population of galaxies that the earlier image had missed. The faintest objects in the frame were roughly 10 times dimmer than the faintest objects detected in 1995, and those objects were overwhelmingly small. They were compact, irregular, and often distorted, caught in the process of forming their first stars or colliding with neighbours. Many appeared to be building blocks rather than finished galaxies, fragments that would later merge and combine over billions of years to create the large spirals and ellipticals visible in the modern universe. The ultra-deep field demonstrated that the deeper you looked, the more the universe changed in character. The present-day cosmos, with its stately spirals and giant elliptical galaxies, was the product of billions of years of merging, growing, and assembling. The early universe was a crowded nursery of small, chaotic structures jostling for space. Astronomers used the ultra-deep field to refine the galaxy count. Extrapolating across the full sky produced estimates in the range of 100 to 200 billion galaxies. The number depended on how faint a galaxy had to be before it was excluded from the count, and on how galaxy populations were modelled at the dimmest extremes. But even the most optimistic extrapolation from the ultra-deep field was an undercount, and everyone knew it. The image showed galaxies at its detection limit as fragile wisps barely distinguishable from random noise. Just below that limit, invisible by the slimmest possible margin, more galaxies certainly existed. The question remained the same as it had been after the original deep field. How many more were hiding beneath the threshold? In 2009, Hubble received its final servicing mission. Astronauts installed the Wide Field Camera 3, the most advanced imaging instrument ever placed on the telescope. This camera dramatically extended Hubble's sensitivity into the near-infrared, the wavelength range where the most distant galaxies radiate most of their detectable light. With this new instrument, astronomers returned to the ultra-deep field and stared again. Additional observations accumulated over the following years, and in 2012, the team combined a full decade of Hubble data into a single image of unprecedented depth. The result was called the Hubble Extreme Deep Field. It focused on a central portion of the original ultra-deep field, narrowing the area of sky but pushing the exposure time to 23 days of total accumulated observation. More than 2,000 individual frames were combined. The extreme deep field contained approximately 5,500 galaxies in a patch smaller than the head of a pin held at arm's length. Some of the most distant galaxies in the image were seen as they existed just 450 million years after the Big Bang, a time when the cosmos was barely 3% of its current age. Each of these progressively deeper images reinforced the same unsettling trend. Every time astronomers pushed the detection limit farther, they found more galaxies. Not just a few more, substantially more. The faintest bins in every survey were the most populated, suggesting that the galaxy population did not thin out gracefully at low luminosities, but instead continued rising steeply. The universe appeared to contain an enormous reservoir of tiny, dim galaxies that previous instruments had missed entirely. The implication was clear but difficult to quantify. The galaxies visible in even the deepest Hubble images were not the full population. They were the bright tip of a distribution that extended far below the observational floor. This realization set the stage for a landmark study published in 2016 that would detonate the existing galaxy count and replace it with a number so large it stunned even the researchers who calculated it. Christopher Consolis, an astrophysicist at the University of Nottingham, had spent 15 years assembling the data and methods needed to answer the galaxy count question in a fundamentally new way. Rather than simply extrapolating from deep images, his team combined observational data from dozens of surveys spanning different depths, wavelengths, and cosmic distances. They built three-dimensional maps of galaxy distributions at different points in cosmic history, going back to when the universe was less than 1 billion years old. Then they modeled how the galaxy population evolved over time, tracking how the number of galaxies in a given volume of space changed as the universe aged. The technique rested on a mathematical tool called the galaxy luminosity function. This function describes how galaxies are distributed across different brightness levels. At the bright end, galaxies are rare. Giants like the Milky Way and Andromeda represent a small fraction of the total population. Moving toward fainter luminosities, galaxies become progressively more common. The luminosity function rises steeply at the dim end, meaning that small, faint galaxies outnumber bright ones by enormous ratios. The critical question was how steeply this function continued to rise below the detection limits of existing telescopes. If it leveled off quickly, then the unseen population was modest. If it continued climbing, the unseen population was vast. To visualize how this works, imagine a census taker who can only count people standing under streetlights. She walks through a city at night and counts everyone she can see. She finds 10,000 people in the illuminated areas. She knows the city has far more residents than that, but the dark streets and unlit buildings conceal them. To estimate the true population, she needs a model. She studies the illuminated zones and notices a pattern. In the brightest downtown areas, she counts a certain number of people per block. In dimmer residential areas, the count per block drops, but the number of blocks increases. She extrapolates this pattern into the darkness, assuming the ratio of people to illumination holds in the parts of the city she cannot see. Her final estimate depends entirely on how she extends the pattern. If she assumes people thin out quickly in the dark zones, her estimate is conservative. If the pattern holds, the city is far more populated than the lit zones suggest. Consolis and his team performed the astronomical version of this exercise. They measured the galaxy luminosity function at multiple cosmic epochs using the best available data. They found that the function rose steeply at the faint end across all the eras they examined. The rate of increase was consistent enough that they could extrapolate below the detection threshold with reasonable confidence. The extrapolation told them how many galaxies should exist at brightness levels too dim for Hubble or any other telescope to detect directly. The answer was shocking. The observable universe, their analysis concluded, contains approximately 2 trillion galaxies. 2 trillion. That number was 10 times higher than the previous consensus estimate of 100 to 200 billion. It meant that more than 90% of all galaxies in the observable universe had never been directly observed by any human instrument. The result landed with tremendous force. Consolis summarized the finding in terms that captured the scale of the revelation. Over 90% of the galaxies in the universe had yet to be studied. The vast majority of cosmic structure was invisible to the best telescopes ever built. Every deep image, every survey, every painstaking exposure had captured only the brightest fraction of a population that extended far deeper into faintness than anyone had previously measured. 2 critical details made the estimate even more remarkable. First, the 2 trillion figure referred not just to the galaxies visible today, but to the total number that had existed across cosmic history. This distinction mattered enormously because galaxy mergers reduce the count over time. In the early universe, when the cosmos was only 1 billion or 2 years old, galaxies were far more numerous. The volumes of space that Constellis's team examined at high redshift contained roughly 10 times more galaxies per unit volume than the same volumes contained today. Small galaxies were everywhere, colliding and merging at rates much higher than anything seen in the modern cosmos. The merger frequency, 3 billion years after the Big Bang, was approximately 15 times higher than it is today. Over billions of years, this relentless process of collision and combination reduced the total count. 2 small galaxies became 1 medium galaxy. Multiple medium galaxies became 1 giant. The universe was not just expanding, it was consolidating. The number of independent galaxies was shrinking even as the surviving galaxies grew larger and more massive. This meant that the number of galaxies observable at any given moment depends on when you look. If you could have surveyed the universe 10 billion years ago, you would have counted far more galaxies than exist today. The 2 trillion figure represented a kind of cosmic average across all epochs, a total inventory of distinct galactic systems that existed at some point within the observable volume. Today's instantaneous count is lower because mergers have combined many of those early galaxies into the larger structures we see around us now. The second critical detail was the role of definition. What counts as a galaxy? This is not a trivial question. At the massive end of the spectrum, the answer is obvious. The Milky Way is a galaxy. Andromeda is a galaxy. Giant ellipticals containing 1 trillion stars are galaxies. But at the faint end, the boundary blurs. Is a collection of a few million stars held together by a dark matter halo a galaxy? Or is it just a large star cluster? What about an object with only 100,000 stars? What about a diffuse smear of old stars orbiting a clump of dark matter with so few luminous members that it barely registers as a visible structure at all? The Constellis estimate used a mass threshold of approximately 1 million solar masses as the lower limit. Change that threshold and the count changes dramatically. Lower the minimum mass and the number of qualifying objects surges upward. Raise it and the count drops. The total number of galaxies in the universe is not a fixed fact. It is a function of how you define the word galaxy. Despite these caveats, the 2 trillion figure entered the scientific conversation and the public imagination as a new benchmark. Media coverage was enormous. The number appeared in textbooks, documentaries, and popular science articles. It became the answer people cited when asked how many galaxies the universe contained. But even as the figure circulated, challenges to it were already forming. The most significant counterargument arrived in January of 2021 from an unexpected source. NASA's New Horizons spacecraft, famous for its flyby of Pluto in 2015 and its subsequent encounter with a distant object in the Kuiper Belt in 2019, was by then billions of miles from Earth, drifting through the outer reaches of the solar system. At that enormous distance, the sky was 10 times darker than anything Hubble could observe from Earth's orbital neighborhood. The inner solar system is filled with a faint glow called zodiacal light, caused by sunlight reflecting off microscopic dust particles scattered between the planets. This glow contaminates every observation made from near Earth, including Hubble's. New Horizons was far enough from the Sun that this contamination essentially vanished. The spacecraft could measure the true darkness of space with a precision impossible from any location closer to the Sun. A team led by Mark Postman and Todd Lauer at the Space Telescope Science Institute used New Horizons to measure the cosmic optical background, the total amount of light suffusing all of space from every galaxy that has ever shone. If 2 trillion galaxies existed, their combined light output, even accounting for the 90% too faint to see individually, should produce a measurable background glow. The researchers pointed New Horizons at 7 carefully chosen patches of empty sky and measured the ambient light level with extreme care. Their finding undermined the 2 trillion estimate. The cosmic optical background was not bright enough to account for 2 trillion galaxies. The measured glow was consistent with a universe containing far fewer galaxies, perhaps several 100 billion rather than 2 trillion. The light simply was not there. If 90% of the universe's galaxies were hiding below Hubble's detection limit, their collective output should have produced a stronger background signal. Instead, the darkness was deeper than expected. The universe appeared to be less crowded than the Consolis estimate required. Postman summarized the result bluntly. We simply do not see the light from 2 trillion galaxies. The finding did not disprove the Consolis estimate outright, because the two approaches measured different things and relied on different assumptions. The luminosity function extrapolation estimated how many galaxies should exist based on mathematical models of galaxy populations. The cosmic optical background measurement estimated how many galaxies could exist based on the total amount of light in the universe. These are related but not identical questions, and reasonable scientists can look at the same sky and arrive at legitimately different answers depending on which method they trust more. The disagreement between them pointed to genuine scientific uncertainty about the faint end of the galaxy population. There were several possible explanations. Perhaps the luminosity function did not rise as steeply below Hubble's detection limit as the Consolis model assumed. If the function flattened or turned over at very low luminosities, the population of unseen dwarfs would be smaller than predicted, and the cosmic background would match what New Horizons observed. Alternatively, the faintest galaxies might be so extraordinarily dim that even their collective contribution to the background was negligible. A galaxy containing only a few thousand stars produces so little light that trillions of such objects might still not add up to a detectable glow. In that case, the 2 trillion figure could be correct, or even an undercount, while still being consistent with a dark sky. A third possibility involves systematic uncertainties in the New Horizons measurement itself. Subtracting every other source of stray light from the cosmic background signal, foreground stars, diffuse galactic emission, residual zodiacal light, instrumental artifacts, is extraordinarily difficult. Small errors in any of those subtractions could shift the result enough to change the implied galaxy count. The tension between these estimates remains unresolved. Some researchers favour a number closer to several hundred billion. Others argue that the 2 trillion figure is conservative, and that the true count, including ultra-faint dwarfs below any current detection limit, might be considerably higher. One analysis suggested that when the smallest dwarf galaxies are included, with roughly 30 to 100 such dwarfs for every large galaxy like the Milky Way, the total might range anywhere from 6 to 20 trillion. The uncertainty spans more than an order of magnitude. The honest answer to how many galaxies exist in the observable universe is that nobody knows. What scientists have is not a number. It is a range, and the range is disturbingly wide. This is not a failure of science. It is the expected consequence of trying to count objects that are, by definition, too faint to count. The galaxy population extends downward into dimness without any known flaw. Every improvement in telescope sensitivity has revealed more galaxies, and there is no observational evidence that the population terminates at any specific brightness level. The faintest galaxies discovered so far are always found right at the detection limit of whatever instrument is searching for them, suggesting that still fainter ones exist just beyond reach. The count is limited not by the universe, but by the instruments. This was the situation when the most powerful space telescope ever constructed opened its eyes. The James Webb Space Telescope launched in December of 2021 aboard an Ariane 5 rocket and travelled to a gravitationally stable point called the Lagrange point, roughly 1 million miles from Earth, on the side opposite the Sun. Its primary mirror, 6.5 meters across, collected more than 6 times as much light as Hubble's 2.4 meter mirror. More critically, Webb was optimized for infrared wavelengths, the part of the spectrum where the most distant galaxies radiate most of their detectable energy. The expansion of the universe stretches light from early galaxies into longer and longer wavelengths, shifting it out of the visible range and into the infrared. Hubble could detect some of this infrared light but was not designed for it. Webb was built specifically to capture what Hubble could not. The telescope's first deep image, released in July of 2022, stared at a galaxy cluster called SMACS 0723 and revealed thousands of galaxies in a sliver of sky, including faint objects at extreme distances that had been invisible to every previous observatory. The image immediately demonstrated Webb's ability to peer deeper into cosmic time than Hubble ever could. Subsequent surveys pushed further still. But what stunned astronomers was not merely that Webb saw more distant galaxies. It was how many bright galaxies it found in the early universe. Standard models of galaxy formation predicted that the first galaxies should be small, faint, and rare, fragile structures just beginning to assemble in the darkness. Webb found the opposite. It discovered galaxies at extreme distances that were unexpectedly luminous, unexpectedly massive, and unexpectedly well-organized. Some appeared to contain billions of stars at a time when theory said they should barely have begun forming. The abundance of these bright early galaxies exceeded predictions by large margins. More than 100 relatively bright galaxies turned up in the very early universe compared to what pre-Webb models expected. This posed a new kind of problem for the galaxy count. If bright galaxies were more common in the early universe than anticipated, the faint population at those same epochs might be even larger than current models predicted. Webb was revealing the upper end of the early galaxy population. The lower end, the swarms of faint dwarfs that should have vastly outnumbered those bright objects, remained invisible even to Webb's extraordinary instruments. The early universe was turning out to be busier, more productive, and more crowded than anyone had assumed. Every observation pushed the inferred total upward. Large survey programs expanded the scope of what Webb could reveal. The Cosmos Webb Survey, the largest general observer program in Webb's first observing cycle, covered more than half a square degree of sky with its near-infrared camera and discovered more than 780,000 galaxies in that single field. These included faint objects at enormous distances, galaxies with extended halos of starlight barely visible above the background, and candidates for some of the most distant galaxies ever identified. The sheer volume of data was staggering. Each new survey added hundreds of thousands of galaxies to the catalogue. Each addition pushed the boundary of the known universe outward and downward into fainter territory. But Webb also introduced a humbling realization. Even with a mirror nearly 3 times the diameter of Hubble's and detectors tuned specifically for the infrared universe, the telescope was still not reaching the bottom of the galaxy population. The faintest objects in Webb's deepest images appeared at the very edge of detectability, just as the faintest objects in Hubble's deepest images had appeared at the edge of Hubble's detectability. The pattern that had held since the original deep field in 1995 continued without deviation. Push the instruments harder, and the universe delivers more galaxies. There is always another layer below. Think of it as an archaeological dig. Each generation of astronomers sifts through a deeper layer of cosmic soil, uncovering objects that were buried below the previous generation's reach. The original deep field dug down one level and found 3,000 galaxies. The ultra-deep field dug deeper and found 10,000. The extreme deep field went deeper still. Webb dug further than all of them, and every layer contained more objects than the one above it. There is no evidence of bedrock. No layer has come back empty. The universe keeps yielding more structure at every depth that science has managed to probe. This open-ended quality is what makes the galaxy count so fundamentally different from other cosmic numbers. The speed of light is a fixed value. The age of the universe is measured to a precision of fractions of a percent. The temperature of the cosmic microwave background is known to 5 decimal places, but the number of galaxies is not a single, stable quantity waiting to be pinned down. It is a moving target that changes with every improvement in technology, every shift in definition, and every new theoretical understanding of how galaxies form and evolve. The 2 trillion estimate, the several hundred billion estimate, the 6 to 20 trillion estimate, these are not competing answers to one question. They are answers to slightly different questions asked with different assumptions about what counts, what is visible, and what lies beyond the horizon of current observation. What they share is a common implication, and it is this implication that transforms the galaxy count from a technical debate into something with genuine power to reshape how we understand reality. The implication is that most of the galaxies in the universe are invisible, not because they are hidden behind obstacles, not because they are cloaked by some exotic process, simply because they are too faint, too small, and too distant for any telescope yet built to detect them. The majority of cosmic structure exists below the floor of human observation. We are not looking at a universe and seeing most of it. We are looking at the luminous surface and inferring an ocean of darkness beneath. This realization changed the question. The issue was no longer how many galaxies we could count. It was how many galaxies we were fundamentally unable to count, and whether there was any limit to how far the invisible population extended. And answering that required understanding the galaxies themselves, the faint, tiny, easily overlooked objects that made up the vast, unseen majority of cosmic structure. Those galaxies were about to become the most important population in the universe. The galaxies we know best are the ones that are easiest to see. Grand spirals with sweeping arms, massive ellipticals glowing with the combined light of trillions of ancient stars, bright starburst systems flaring with the energy of violent collisions. These are the galaxies that fill textbooks, posters, and documentary footage. They dominate deep field images with their size and luminosity, and they represent a tiny, utterly unrepresentative fraction of the total galactic population of the universe. The most common type of galaxy in the cosmos is something most people have never heard of: dwarf galaxies. These are small, dim, low-mass systems containing anywhere from a few 100,000 to a few billion stars. Some are so faint that their total luminosity is less than 1/10,000th of the Milky Way's output. They produce so little light that at cosmological distances they vanish entirely, falling below the detection threshold of even the most sensitive instruments ever built. Yet they almost certainly constitute the overwhelming majority of all galaxies that exist. By every measure available to modern astronomy, faint dwarfs outnumber large galaxies by enormous ratios. Some estimates suggest there are 30 small galaxies for every large one. Other analyses push that figure to 50, or 70, or even 100. The exact ratio remains uncertain because the faintest dwarfs are the hardest to find. But every survey that looks for them finds more than expected, and no survey has ever found evidence that the population terminates at any specific size. This is not a minor statistical footnote. It is the central fact that determines the total galaxy count, and it transforms the question of how many galaxies exist from a straightforward counting exercise into a problem about the limits of observation itself. Consider our own local group, the small gravitational family of galaxies that includes the Milky Way, Andromeda, and roughly 80 known companions. For decades, the local group appeared to contain only a few dozen members. The large galaxies were obvious. Andromeda and the Milky Way dominate the group with their combined hundreds of billions of stars. The Magellanic Clouds, visible to the naked eye from the southern hemisphere, were identified centuries ago. A handful of brighter dwarf galaxies, the Sagittarius dwarf, the Sculptor dwarf, the Fornax dwarf, were found through careful photographic surveys in the mid-20th century. The known population of the local group seemed complete, or at least nearly so. Then in 2005, astronomers mining data from the Sloan Digital Sky Survey began finding objects that nobody had noticed before. They were not hiding behind dust clouds or lurking at enormous distances. They were orbiting the Milky Way at distances of a few 100,000 light-years, cosmically close, practically in our backyard. But they were so dim that they had escaped detection until a survey sensitive enough to pick them up finally existed. These were the ultra-faint dwarf galaxies, a population of objects so small and so sparse that they barely registered above the background scatter of ordinary field stars. The discoveries came in rapid succession. Segway 1, Segway 2, Carina, Tucana, and dozens of others emerged from the survey data over the following years. Each one was smaller and dimmer than the last. Segway 1 holds the record as the faintest known galaxy, a collection of roughly 1,000 stars producing a total luminosity equivalent to about 300 suns, not 300 billion, 300. This object, gravitationally bound in a dark matter halo, vastly more massive than its visible content, qualifies as a galaxy under most working definitions. And it was found orbiting the Milky Way, essentially next door by cosmic standards. Its existence raises an immediate and unsettling question. If objects this faint can hide within our own galactic neighborhood for decades, how many similar objects exist throughout the universe that we have absolutely no hope of ever detecting? The answer, according to the best available models, is staggering. If the ratio of faint dwarfs to large galaxies observed in the local group holds across the wider cosmos, then the invisible population of galaxies dwarfs the visible one by factors that reshape the entire count. For every Milky Way-sized galaxy in the universe, there may be 50 to 100 ultra-faint companions too dim to see at any significant distance. Multiply that ratio by the billions of large galaxies we can detect, and the total soars into the trillions or tens of trillions. The universe is not sprinkled with galaxies, it is saturated with them. The problem is that most of them are essentially invisible beyond the nearest cosmic distances. Trying to count the total galaxy population using only the galaxies we can directly observe is like conducting a census of all wildlife on Earth by counting only the elephants. Elephants are large, conspicuous, and easy to spot. You can count them from aircraft, track them with satellites, and estimate their global population with reasonable confidence. But the total number of animal species on the planet is not dominated by elephants. It is dominated by insects, by microorganisms, by creatures too small and too numerous for any individual level census to capture. The visible galaxies are the elephants of the cosmos. The ultra-faint dwarfs are the insects. And just as entomologists estimate insect populations through sampling and statistical modelling rather than individual counting, astronomers must estimate the faint galaxy population through indirect inference rather than direct detection. The galaxy luminosity function, the mathematical curve describing how galaxies distribute across brightness levels, becomes the critical tool here. What Consolis's team modelled at a distance, local group observations test up close. And the local evidence is unambiguous. The function does not flatten, it keeps climbing. Every survey that reaches to lower luminosities within our cosmic neighbourhood discovers more dwarf galaxies than the one before. The Sloan Digital Sky Survey found ultra-faint dwarfs that earlier surveys had missed. Subsequent campaigns with deeper sensitivity found fainter ones still. The pattern holds without exception. No survey has reached a luminosity where the population of small galaxies begins to thin out or turn over. The bottom of the distribution has never been found. This has a striking mathematical consequence. When the faint end of a distribution rises steeply, the total count becomes dominated not by the conspicuous objects at the top, but by the invisible objects at the bottom. The giants are rare and bright. The dwarfs are common and dark. As a result, the true galaxy count depends almost entirely on how far down the function extends before it finally levels off. If it continues rising for just a few more orders of magnitude below current detection limits, the total number of galaxies could be 10 or 50 times higher than any estimate based on what we can see. The answer is not set by the galaxies we observe. It is set by whatever process eventually stops the smallest halos from forming stars at all. And that process, if it exists, has left no observational signature that any telescope has yet detected. And here is where a remarkable twist enters the story. The very first galaxies in the universe may have actively prevented later ones from forming. This process, called reionization suppression, represents one of the most fascinating feedback loops in all of cosmic evolution. In the first few 100 million years after the Big Bang, the universe was filled with neutral hydrogen gas, dark and opaque to certain wavelengths of light. When the earliest galaxies ignited their first stars, those stars were intensely hot. They poured ultraviolet radiation into the surrounding gas, stripping electrons from hydrogen atoms and ionizing the intergalactic medium. This transformation, known as the epoch of reionization, flooded the cosmos with a bath of energetic ultraviolet photons that persists to this day, though at much lower intensity. That radiation bath had a devastating effect on the smallest dark matter halos. Before reionization, gas could fall into halos of almost any size, cool down, and begin forming stars. The universe was hospitable to galaxy formation at every scale. But once the ultraviolet background established itself, everything changed. The radiation heated the intergalactic gas to temperatures of tens of thousands of degrees. Hot gas has too much thermal energy to collapse into shallow gravitational wells. Small halos, the ones with the weakest gravitational pull, could no longer capture enough gas to form stars. The very process that created the first galaxies raised the barrier for all subsequent galaxy formation. The first generation pulled the ladder up behind them. This suppression mechanism means the galaxy count is shaped not only by what formed, but by what was prevented from forming. Countless dark matter halos that would have become galaxies in a pre-reionization universe instead remain dark, empty of stars, invisible to every telescope. They exist as gravitational structures, detectable only through their influence on nearby matter, but they never became galaxies in any observational sense. The total number of galaxies is therefore lower than the total number of halos. and the gap between those two numbers depends on the intensity and timing of the ultraviolet background, factors that are still being refined by observation and simulation. The implications for the galaxy count are profound. If reionization suppressed galaxy formation in the smallest halos, then the faint end of the luminosity function should eventually turn over. Below some critical luminosity, galaxies should become rarer rather than more common, because the halos that would have hosted them were sterilized by ultraviolet radiation before they could form stars. Finding this turnover point would place a genuine flaw on the galaxy count, but so far, no observation has detected it. Either the turnover occurs at luminosities even fainter than the faintest galaxies currently known, or the suppression was less complete than models suggest, allowing some small halos to form stars despite the radiation. Until the turnover is found, the faint end remains an open question, and the total galaxy count remains unconstrained from below. Adding to the complexity is the fact that galaxies are not permanent fixtures. They evolve, merge, and transform over cosmic time, and the merging process has a direct and dramatic effect on the galaxy count. The early universe contained far more galaxies per unit volume than the present-day cosmos. Those early galaxies were smaller, closer together, and colliding constantly. Over billions of years, that relentless consolidation devoured entire populations of independent systems, absorbing them into the larger structures we observe today. The merging did not just reduce the count, it erased individual galactic histories. Every merged galaxy lost its identity, its independent orbit, its distinct population of stars. What had been 2 or 3 or 10 separate systems became one, and the census dropped accordingly. The galaxies that survive to the present are the winners of a billions-year process of gravitational cannibalism, and the losers are gone, folded into the bodies of their conquerors. This means the number of galaxies in the universe is not a fixed quantity. It changes with cosmic era. If you could have counted galaxies when the universe was 2 billion years old, the total would have been much higher than any count performed today. The Constelli's estimate of 2 trillion galaxies was, in part, an attempt to capture this time-average total, the number of distinct galactic systems that existed at some point across cosmic history. The present-day count, a snapshot of how many independent galaxies exist right now, would be lower because many of those early systems have since merged. But even the present-day count depends on what you count as a galaxy, which brings the problem to its most fundamental level. What is a galaxy? The question sounds absurd. Everyone knows what a galaxy is, a large collection of stars, gas, dust, and dark matter bound together by gravity. But this intuitive definition breaks down at the edges. At the massive end, the classification is straightforward. Nobody disputes that the Milky Way, or Andromeda, or the giant elliptical galaxies in the Virgo cluster are galaxies. They contain hundreds of billions of stars, span tens or hundreds of thousands of light years, and sit at the centers of massive dark matter halos. The term galaxy applies to them without controversy. But at the small end, the situation dissolves into ambiguity. Consider an object containing 10 million stars embedded in a dark matter halo. Is that a galaxy? Most astronomers would say, yes. What about an object with 1 million stars? Probably still a galaxy. 100,000 stars. This is where the argument begins. The globular clusters orbiting the Milky Way contain hundreds of thousands of stars, but they are not classified as galaxies. They lack significant dark matter. They formed within the Milky Way rather than independently. Their internal chemistry follows patterns distinct from dwarf galaxies, but some of the ultra-faint dwarf galaxies discovered in recent years contain fewer stars than large globular clusters. The distinction rests not on star count, but on whether the object is embedded in its own dark matter halo and formed as an independent structure in the early universe. This definitional ambiguity matters enormously for the total count. If you define galaxy generously, including every self-gravitating collection of stars in its own dark matter halo, regardless of how few stars it contains, the number skyrockets. If you impose a minimum mass or luminosity threshold, the number drops. The 2016 estimate used a threshold of approximately 1 million solar masses. Lower that threshold and the count rises dramatically. Raise it and the count falls. There is no universally agreed standard. Different research groups use different definitions, and the resulting galaxy counts can differ by factors of 5 or 10, depending on where the cutoff is placed. Surface brightness adds yet another layer of difficulty, and it is a problem that operates entirely separately from faintness. A galaxy's surface brightness is a measure of how much light it produces per unit area of sky. This distinction matters because a galaxy can be intrinsically luminous, containing hundreds of billions of stars, and still be nearly undetectable if those stars are spread across an unusually large volume of space. The total light might be enormous, but the light per square arc-second of sky is so low that it disappears into the background noise. The galaxy is not faint in the way a dwarf galaxy is faint. It is dim in the way a fog is dim, spread so thin you can look right through it without noticing it is there. The most dramatic example of this phenomenon is a class of objects called giant low-surface brightness galaxies. Malin 1, discovered in 1987, is the most famous. It is an enormous spiral galaxy with a visible disk extending over 500,000 light-years, several times the diameter of the Milky Way. It contains billions of stars. By any reasonable definition, it is a giant galaxy. Yet it went undetected until the late 20th century, because its stars are distributed so sparsely that its surface brightness falls below the threshold of most surveys. Malin 1 hides not through faintness but through diffuseness. Its light is real and substantial, but it is spread across so much sky that no individual patch of it rises above the noise. How many galaxies like Malin 1 exist? Nobody knows. Standard surveys are optimized to detect compact, high-surface brightness objects that concentrate their light into a small area and produce strong signals relative to the background. Extended, diffuse galaxies are systematically missed because their signal is spread across too many pixels. Algorithms designed to identify galaxies in survey images typically set a surface brightness threshold below which an object is discarded as noise. Every galaxy that falls below that threshold, no matter how large or how luminous in total, is invisible to the survey. It does not appear in the catalogue. It is not counted. Some estimates suggest that up to half of all galaxies at certain luminosity levels may fall below current surface brightness detection limits. These are not small objects. Some could be as large as the Milky Way or larger. They are simply ghosts, too thinly spread to register on most detectors. Correcting for this population would increase the galaxy count substantially, and it would increase the total amount of starlight in the universe, which directly affects the cosmic optical background measurement that the New Horizons team used to challenge the 2 trillion estimate. If a significant population of large, low-surface brightness galaxies has been systematically missed, the background could be brighter than current models predict, which would allow for a higher total galaxy count. The surface brightness problem does not just add galaxies to the census. It potentially resolves part of the tension between competing estimates. When you combine the problem of faint dwarfs, the problem of surface brightness, the problem of reionization suppression, the problem of mergers over cosmic time, and the problem of definitions, the galaxy count ceases to be a single number and becomes a range of plausible values stretching across orders of magnitude. The honest scientific answer is that the observable universe contains somewhere between several hundred billion and perhaps 20 trillion galaxies, depending on how faint a galaxy can be and still qualify as a galaxy, and on how many of the smallest, dimmest, most diffuse objects exist below current detection thresholds. The uncertainty is enormous, and it is not shrinking as quickly as anyone would like. The James Webb Space Telescope was supposed to narrow this uncertainty, and in some ways it has, but in other ways it has made the problem even more complex. When Webb turned its infrared eyes toward the earliest cosmic epochs, it found a universe that did not match the predictions of standard galaxy formation models. The expectation, based on the leading Lambda CDM cosmological framework, was that the first galaxies should be small, sparse, and feeble. They should have been assembling gradually from primordial gas, building up their stellar populations slowly over hundreds of millions of years. Webb found galaxies that defied this timeline. Objects existing when the universe was only 300 to 500 million years old appeared far more luminous, more massive, and more structurally developed than theory predicted. Some contained stellar populations that seemed to require faster assembly rates than standard models could easily produce. The program known as JDS, the James Webb Space Telescope Advanced Deep Extragalactic Survey, provided some of the most detailed observations of these early galaxies. It confirmed spectroscopically that several galaxies exist at redshifts beyond 13, corresponding to a time when the universe was less than 350 million years old. In 2025, a galaxy designated MOMZ14 was confirmed as the most distant galaxy known, observed as it existed roughly 280 million years after the Big Bang. This object was small, roughly 50 times smaller than the Milky Way, but it was actively forming stars and already contained detectable amounts of elements like nitrogen and carbon that are produced by stellar nucleosynthesis. It should not have been there, at least not according to the simplest versions of existing theory. The excess of bright galaxies at early times has sparked intense debate about what it means. Some researchers argue that star formation in the early universe was burstier than assumed, with galaxies cycling through intense episodes of stellar production, followed by quiescent periods, making them appear brighter on average during their active phases. Others suggest that the initial mass function of stars was different in the early cosmos, with a higher proportion of massive, luminous stars forming from the metal-poor primordial gas. Still others propose that the efficiency of star formation was systematically higher in the extreme environments of the early universe, where gas densities were greater and cooling processes operated differently. What matters for the galaxy count is the implication hidden beneath these debates. If the bright end of the early galaxy population exceeded expectations, the faint end almost certainly did as well. The bright galaxies Webb detected were the most luminous members of their generation, the objects easiest to find. For every bright galaxy Webb spotted at extreme redshift, there should have been dozens or hundreds of fainter ones below even Webb's detection threshold. The early universe was not just busier than expected at the bright end, it was likely far busier at the faint end too. And those faint early galaxies, the ones that no telescope has yet seen, contributed to the total galaxy count across cosmic history. The Cosmos Webb survey reinforced this picture from a different angle. By covering a wide area of sky rather than a tiny deep pencil beam, it catalogued more than 780,000 galaxies in a single field, including many with extended low surface brightness features that previous surveys would have missed. Some of these galaxies displayed faint outer halos of starlight that extended far beyond their visible cores. Earlier studies using Hubble had shown that ignoring these faint stellar halos could cause astronomers to miss significant amounts of light, equivalent to the output of 1 trillion stars across the full survey. The implication was that even galaxies bright enough to detect individually were being measured incompletely. Their true extent was larger, and their true luminosity higher than standard analysis pipelines reported. The problem compounds at every level. Faint dwarfs are too dim to detect at cosmological distances. Low surface brightness galaxies are too diffuse to distinguish from background noise. Galaxies at extreme redshifts are too far away for their light to arrive in detectable quantities. Galaxies that merged billions of years ago no longer exist as independent objects. Galaxies that might have formed were prevented from doing so by the ultraviolet radiation that the first generation of stars unleashed. And the boundary between what counts as a galaxy and what does not remains blurry enough that the total depends on where you draw the line. Each of these factors individually introduces substantial uncertainty into the count. Together, they create a situation where the true number of galaxies is only loosely constrained by observation. Attempting to take an inventory of the universe's galaxy population based on what our telescopes can see is like trying to assess the full contents of an ocean by cataloguing only what floats on the surface. You can count the visible objects with precision. You can measure their sizes and shapes and positions. You can extrapolate from the density of surface objects to estimate what lies beneath. But you are fundamentally limited by the fact that the vast majority of the ocean's contents exist at depths you cannot reach. The surface inventory, no matter how meticulous, captures only a fraction of the total, and the fraction it misses is not randomly distributed. It is systematically biased toward the objects least like the ones you can see, the smallest, the dimmest, the most diffuse, the most distant, and the most ancient. This systematic bias is not a flaw in any particular telescope or survey. It is built into the physics of observation. Light spreads out as it travels. The farther a source is, the fainter it appears. Below a certain brightness, no amount of exposure time can pull a signal from the noise. Below a certain surface brightness, no camera can distinguish a galaxy from the empty sky. Below a certain angular size, no telescope can resolve a galaxy from a point source. These limits are not technological, they are physical. Improving instruments pushes the limits further, but it does not eliminate them. Every telescope, no matter how powerful, has a detection flaw, and below that flaw the invisible majority resides. The next generation of observatories will push the detection flaw lower than any instrument operating today. New wide-field surveys will cover thousands of times more sky than Hubble's narrow deep fields, discovering millions of galaxies that pencil beam observations missed. New infrared programs will reach deeper into the early universe, hunting for the faintest objects at the highest redshifts. New space missions designed to map the geometry of the cosmos will detect galaxies at distances that previous wide-area surveys could not reach. Each new capability will add to the count. Each addition will demonstrate once again that the previous count was incomplete. But these missions, as powerful as they will be, face the same fundamental constraints that have limited every previous survey. But there is a deeper limit that no telescope can overcome. It is not a limit of sensitivity or resolution or exposure time. It is a limit imposed by the universe itself, the observable universe, the region of space from which light has had time to reach us since the cosmos began, has a finite size. It extends approximately 46.5 billion light-years in every direction. Beyond that boundary, more universe almost certainly exists, but no light from those regions has reached us and no signal from them ever will within any meaningful human time frame. Every galaxy count ever performed, every estimate ever published, every survey ever conducted applies only to this observable volume. The total universe, whatever its true extent, may contain galaxies in numbers that make even the most generous estimates of the observable population look negligible. And it is this boundary, the edge of the observable universe itself, that transforms the galaxy count from a difficult measurement into something far stranger. A question about the fundamental limits of knowledge. What lies beyond the horizon, and why the answer may be permanently unknowable, is where the story turns next. Everything counted so far, every galaxy in every deep field, every dwarf satellite orbiting the Milky Way, every faint smudge in every survey, every estimate extrapolated from every luminosity function, all of it applies to one region, the observable universe, a sphere of space centered on Earth extending approximately 46.5 billion light-years in every direction. This is not the universe. It is the fraction of the universe from which light has had time to reach us since the cosmos began 13.8 billion years ago. Beyond this sphere, more space almost certainly exists. More matter, more structure, more galaxies, but no light from those regions has arrived at Earth. No signal from them has ever registered on any instrument. No information of any kind has crossed the boundary. The observable universe is not a physical edge. It is an informational horizon, a limit on what we can know rather than what exists. The reason this horizon exists is rooted in the most basic facts of physics. Light travels at a finite speed, roughly 186,000 miles per second. The universe has existed for a finite time, approximately 13.8 billion years. In that time, light from the most distant visible sources has traveled an enormous distance, but not an infinite one. The expansion of space during the journey stretched the distance between source and observer, which is why the observable sphere has a radius of 46.5 billion light-years rather than 13.8 billion. Objects that emitted their light shortly after the Big Bang were much closer when they emitted it. Cosmic expansion carried them outward during the billions of years it took their photons to reach Earth. The objects themselves now sit far beyond the distance their light has travelled, stretched to the edge of the observable volume by the relentless expansion of space. This creates a peculiar and deeply counterintuitive situation. The most distant galaxies we can see are not at the edge of reality. They are at the edge of visibility. Beyond them, space continues. The laws of physics do not change at the horizon. Matter does not cease to exist. The cosmic web of filaments and voids does not terminate. Everything we understand about the large-scale structure of the universe indicates that it extends far beyond what we can observe, and that the regions beyond our horizon look, on average, very much like the regions within it. The observable universe is not a special zone. It is a sample, one patch of a vastly larger whole. How much larger? This is one of the most important questions in cosmology, and the honest answer is that nobody knows with certainty, but there are strong constraints. The geometry of space, as measured with extraordinary precision by satellites that mapped the cosmic microwave background, appears to be flat, not curved like the surface of a sphere, not warped like a saddle, flat, or so close to flat that no curvature has been detected across the entire observable volume. This flatness has a direct implication for the size of the total universe. If space were noticeably curved, it would mean the universe was finite and relatively small, and the curvature would show up as subtle distortions in the patterns of the cosmic microwave background. The absence of detectable curvature means either the universe is infinite, or it is so much larger than the observable volume that its curvature is undetectable at our scale. Statistical analyses of the cosmic microwave background data from the Planck satellite, combined with other cosmological measurements, have placed lower bounds on the total size. One widely cited analysis concluded that the universe is at least 250 times larger in radius than the observable volume. If correct, this means the total universe contains at least 15 million times the volume of the observable sphere. For every galaxy within our horizon, at least 15 million comparable volumes of space exist beyond it, each presumably containing a similar density of galaxies. The numbers become incomprehensible almost immediately. If the observable universe contains 2 trillion galaxies and the total universe is 15 million times larger, the implied total exceeds 30 quintillion galaxies. If the observable count is closer to several hundred billion, the total beyond the horizon still runs into the thousands of trillions. And if the universe is infinite, as flat geometry permits, the number of galaxies is infinite as well. These figures are not meant to be taken as precise counts. They are meant to illustrate how completely the observable universe is dwarfed by what may lie beyond it. The galaxies we have spent decades counting and cataloguing, the galaxies whose light fills our deepest images, represent a sample so small relative to the possible total that the ratio approaches zero. We are not observing the universe. We are observing a window into it, a narrow, luminous sliver, defined not by the extent of reality but by the speed of light and the age of time. The cosmic microwave background radiation provides the most dramatic illustration of this boundary. This faint glow, first detected accidentally by Arno Penzias and Robert Wilson in 1964, fills every direction of the sky at a nearly uniform temperature of approximately 2.7 Kelvin, just above absolute zero. It is the oldest light in the universe, released when the cosmos was only 380,000 years old. Before that moment, the universe was an opaque fog of superheated plasma. Protons and electrons existed as separate particles, and their constant interactions scattered photons so efficiently that light could not travel in a straight line. The universe was brilliant but blind. Nothing could be seen through the glowing haze. When the cosmos cooled enough for protons and electrons to combine into neutral hydrogen atoms, the scattering stopped. Space became transparent. Light was released in every direction and has been traveling freely through the expanding universe ever since. That light, stretched by billions of years of cosmic expansion from its original visible wavelengths into the microwave portion of the spectrum, is what we detect today as the cosmic microwave background. This radiation forms a wall, not a physical wall, but an observational one. It is the farthest surface from which electromagnetic radiation can reach us. Beyond it, the universe existed, but in a state that was opaque to light. No photon from before that moment of recombination can reach any telescope. The cosmic microwave background is the ultimate limit of optical and infrared astronomy. Every galaxy, every star, every structure that formed after that moment and within the observable volume can, in principle, be detected. Everything before it and beyond it is hidden. The satellites that mapped this ancient light, COBE in 1989, the Wilkinson Microwave Anisotropy Probe in 2001, and Planck in 2009, measured temperature variations across the sky at the level of a few hundred thousandths of a degree. These tiny fluctuations are not noise. They are the seeds of everything. Slightly warmer spots correspond to regions that were fractionally denser than average in the infant universe. Those regions attracted more matter through gravity, eventually collapsing into the galaxies, clusters, and filaments of the cosmic web. Slightly cooler spots correspond to regions that were less dense, the voids that would remain relatively empty for billions of years. The pattern of fluctuations encodes the initial conditions from which all cosmic structure grew. This means that the galaxy count, the number that astronomers have been chasing for decades, is a direct consequence of quantum fluctuations that occurred in the first fraction of a second after the Big Bang. Random variations in the density of the primordial cosmos, amplified by gravity over billions of years, determined where galaxies would form, how many would form, and how large they would grow. The answer to how many galaxies exist was set in motion before atoms existed, before light existed, before space itself had expanded to any meaningful scale. The count was encoded in the initial conditions of the universe and has been playing out ever since. But encoded does not mean knowable. The initial conditions within our observable volume produce the galaxies we can count and model. The initial conditions beyond the horizon produce galaxies we will never see. And those conditions were drawn from the same statistical distribution, the same physics, the same quantum processes. There is every reason to believe that the universe beyond our horizon is as rich, as structured, and as full of galaxies as the universe within it. But believing and knowing are different things, and the horizon ensures that belief is all we will ever have. This situation is made worse by the fact that the observable universe is not growing in a meaningful sense. It is true that the horizon technically expands every day as light from slightly more distant regions arrives for the first time, but cosmic expansion is accelerating. The discovery in 1998 that the expansion of the universe is speeding up rather than slowing down, driven by a mysterious component called dark energy, changed the long-term outlook for cosmic observation permanently. Dark energy comprises approximately 68% of the total energy content of the universe. It behaves like a pressure built into the fabric of space itself, pushing everything apart with increasing force. As expansion accelerates, distant galaxies are carried away from us faster and faster. Galaxies that are currently visible will eventually cross a threshold beyond which their light can no longer outrun the expansion of the intervening space. Their photons will be stretched to infinite wavelength and zero energy. They will fade from view, not because they cease to exist, but because the space between us and them is expanding too rapidly for any signal to bridge the gap. The galaxies will still be there. They will still shine, but their light will never reach us again. This process has already begun. The most distant galaxies currently visible are receding at speeds that approach, and in some cases exceed the speed of light. They are visible only because their light began its journey toward us when they were much closer, before expansion carried them to their current extreme distances. No new light from these galaxies will ever arrive. The photons they emit today are born into a region of space that is expanding away from us faster than the photons can travel toward us. Those galaxies have effectively disappeared from our future sky, even though we can still see their ancient light. Over the next tens of billions of years, this process will accelerate. The Virgo cluster, 54 million light-years away, will eventually be carried beyond the horizon. The cosmic web that currently stretches across the observable volume will thin and fragment as expansion pulls its filaments apart. Galaxies outside the local group will fade one by one, their light redshifting into invisibility. In approximately 2 trillion years, according to current models, the only galaxies visible from our location will be the merged remnant of the Milky Way and Andromeda, a single giant elliptical galaxy, sometimes called Milkomeda, surrounded by a handful of surviving dwarf companions. The rest of the universe will have vanished behind an impenetrable curtain of expansion. Imagine a civilization arising in that distant future. Their astronomers would look out at a sky containing one galaxy, their own, surrounded by absolute emptiness. No other galaxies visible in any direction. No faint smudges in deep exposures. No galaxy clusters. No cosmic web. Just one island of stars in what appears to be an infinite, featureless void. These scientists would have no evidence that other galaxies ever existed. The cosmic microwave background, the ancient light that tells us so much about the Big Bang and the early universe, would be stretched to wavelengths so long that no instrument could detect it. The telltale patterns in that radiation, the patterns that reveal cosmic expansion, the seeds of structure formation, the geometry of space itself, would be erased. Without the cosmic microwave background, there is no observational evidence for a Big Bang. Without distant galaxies, there is no evidence of cosmic expansion. Without expansion, there is no reason to suspect the universe was ever any different from what these future astronomers see around them. A single galaxy in a static void. They would almost certainly develop a cosmology. They would study the stars and gas within their galaxy. They would discover nuclear fusion and stellar evolution. They would measure the motions of stars and calculate the galaxy's mass. But their cosmology would be wrong. They would have no reason to believe that trillions of galaxies once filled the observable sky. They would have no way to discover that the universe began in a hot, dense state and expanded over billions of years. They would have no clue that the void surrounding them was once a crowded, glittering cosmos teeming with structure. The evidence that would have told them the truth would have been carried beyond their horizon by the very expansion they could no longer detect. Their universe would be a lie told by silence, and they would have no way to know it. This thought experiment is not merely a curiosity about the far future. It carries an implication for us right now. If evidence can be erased by the passage of time and the stretching of space, then the question becomes unavoidable. Has any evidence already been erased from our sky? Is there information about the universe that was once available to observers, but has since vanished beyond detection? The answer is almost certainly yes. The cosmic microwave background itself represents a barrier. Everything that happened before recombination, the first 380,000 years of cosmic history, is hidden behind an opaque wall of plasma. The processes that occurred during that era, the formation of the first atomic nuclei, the separation of fundamental forces, the inflationary expansion that may have generated the initial density fluctuations, all of these are inferred rather than observed. They happened, but their direct signatures have been erased or obscured beyond recovery. We deduce them from indirect clues in the same way a detective reconstructs a crime from circumstantial evidence rather than eyewitness testimony. If the universe has already hidden some of its history from us, and if it will hide vastly more in the future, then our current cosmology occupies a specific window of opportunity. We live in an era when enough evidence is still visible to construct a largely accurate picture of cosmic evolution. The cosmic microwave background is still detectable. Distant galaxies are still visible. The expansion of space is still measurable. These clues will not last forever. We are building our understanding of the universe during a finite window of cosmic visibility, and there is no guarantee that the picture we are constructing is complete. It is the best picture the evidence allows, but the evidence is a subset of reality, not reality itself. But the window that future civilizations will lose is not as wide open as we tend to assume, even now, even for us. We treat our current cosmic visibility as comprehensive. It is not. It is partial, biased, constrained by the same physics that will eventually close it all together. We see only the galaxies that are bright enough, close enough, and old enough for their light to have reached us. The faintest dwarfs are invisible. The most diffuse systems are undetectable. The most distant objects are beyond the horizon. The galaxies that merged billions of years ago no longer exist as independent structures. The full population of galaxies that has ever existed in the observable universe is already partly lost to us, erased by time and merger and the relentless stretching of space. What we observe is a fraction of a fraction of a fraction, the visible galaxies within the observable universe within the total cosmos. Standing inside this reality and trying to answer how many galaxies exist is like standing on a hilltop in dense fog and trying to count every tree in the forest. You can see the nearest trees clearly. You can count them with confidence. Farther out, the shapes grow vague. Some trees are visible as dark outlines. Others are hidden entirely. Beyond a certain distance, the fog is absolute, and you see nothing at all. You know the forest continues beyond the fog because you can hear birds, feel the wind, smell the earth. But you cannot count what you cannot see. And the fog is not lifting, it is thickening. The galaxy count is that fog-bound estimate, every number that has ever been published, from the 100 billion estimate derived from the original Hubble Deep Field, to the 2 trillion figure from the Galaxies analysis, to the more recent estimates ranging from several 100 billion to 20 trillion, is a count of trees visible from one hilltop, through one thickness of fog, using one set of eyes. Change the instruments and the count changes. Change the definitions and the count changes. Expand the horizon and the count changes again. The number is real in the sense that it reflects genuine observations and careful science. But it is not final. It has never been final. And it may never be final. What the galaxy count truly measures is not the universe. It measures the boundary between what we know and what we do not know. It quantifies the edge of human observation. Every revision to the number, every upward correction, every new population of faint dwarfs discovered lurking below the previous detection threshold is a statement about how much of reality was previously invisible to us. The count does not tell us how full the universe is. It tells us how limited our view has been. This is why the question matters far beyond its numerical answer. It forces a confrontation with the deepest kind of scientific humility. Astronomy has spent 4 centuries expanding the scope of human knowledge. Galileo showed us the moons of Jupiter. Hubble showed us galaxies beyond the Milky Way. The cosmic microwave background showed us the infancy of the universe itself. Each discovery pushed the boundary outward, revealing more of reality than the previous generation could imagine. But the galaxy count reveals something different. It shows us the boundary itself. It demonstrates that no matter how far we push, the universe extends further. No matter how deep we look, more structure hides below. The boundary is not a problem to be solved. It is a feature of reality. Future telescopes will continue to push. The Nancy Grace Roman Space Telescope will survey vast areas of sky with sensitivity that bridges the gap between Hubble's narrow deep fields and wide shallow surveys. The Vera Rubin Observatory will catalogue billions of objects across the accessible sky. Future web programs will reach deeper into the infrared, hunting the faintest galaxies at the highest redshifts. Proposed next-generation space telescopes with mirrors 10 or 15 meters across could push the detection threshold down by another order of magnitude, revealing populations of ultra-faint galaxies that current instruments cannot touch. Each of these missions will add to the count. Each will demonstrate once again that the previous count was incomplete, but none of them will reach the bottom. The physics of observation guarantees that a flaw will always exist below the threshold of any conceivable instrument. The expansion of the universe guarantees that a horizon will always limit the volume we can survey. The evolution of galaxies through mergers guarantees that the historical count will always exceed the present-day count, and the probable vastness of the universe beyond the observable horizon guarantees that whatever we count within our sphere represents only a sample of a potentially infinite whole. The answer to how many galaxies exist in the universe is not 2 trillion. It is not 200 billion. It is not 20 trillion. The answer is that nobody knows, and the range of plausible values spans from hundreds of billions to infinity depending on how the question is framed. This is not a failure. It is the most honest answer science can give. It reflects the genuine state of knowledge and the genuine limits of observation. Any single number presented without this context is misleading. The universe does not owe us a tidy answer. What we can say with confidence is this: every time humanity has developed a better way to look at the sky, the universe has turned out to contain more galaxies than the previous generation believed. The pattern has held without exception for a century. From Edwin Hubble's first confirmation that galaxies beyond the Milky Way existed at all, through the photographic surveys of the mid-20th century, through the Hubble Deep Fields and ultra-deep fields, through the James Webb Space Telescope's infrared revelations of the early cosmos, every improvement in capability has delivered the same message. There are more galaxies than you think. There have always been more galaxies than you think. The smallest, faintest, earliest, and most distant galaxies are exactly the ones that are easiest to miss. They are the ones that fall below the detection limit. They are the ones that merged into larger structures billions of years ago and no longer exist as independent objects. They are the ones that sit beyond the observable horizon in regions of space we will never see. They are the ones whose surface brightness is so low that they blend into the background of the sky like pale ink dissolved in dark water. These invisible galaxies are not a minor correction to the visible count. They are the majority. The galaxies we can see are the exception. The galaxies we cannot see are the rule. Consider what this means for the question that opened this story. How many galaxies actually exist in the universe? The question assumed that an answer existed, a number waiting to be discovered, a cosmic census waiting to be completed. But the universe does not work that way. The count depends on what you can detect. It depends on what era you observe. It depends on where you draw the line between galaxy and non-galaxy. It depends on how much of the total universe lies beyond the horizon that physics imposes on every observer everywhere. The question is not unanswerable. It is unanswerable in the way it was asked. The better question, the one that the last century of observation has actually been answering, is how much of the universe remains hidden from us. And the answer to that question has been the same every single time it has been asked. More than we thought. This is the real story of the galaxy count. It is not a story about arriving at a number. It is a story about the progressive discovery that the universe is deeper, richer, and less directly visible than any previous estimate suggested. Every deeper image has revealed more structure. Every better instrument has found more galaxies. Every refined model has pushed the inferred total higher. And there is no sign that this process is approaching an end. The universe keeps yielding more whenever we find better ways to look. The reasonable conclusion is not that we are close to the final answer. The reasonable conclusion is that the final answer may not exist in any form we can express. The night sky appears serene, a few thousand stars visible to the naked eye, a pale band of light marking the plane of our galaxy, a faint smudge in Andromeda if you know where to look. It seems quiet, almost empty, but behind that apparent emptiness, stacked in depth across billions of light years of space and time, galaxies fill the darkness in numbers that have defeated every attempt to count them conclusively. Hundreds of billions that we can directly detect, trillions that models predict below the detection floor, and beyond the cosmic horizon, in the vast majority of the universe that light has not yet had time to reveal, a population of galaxies that may exceed everything within our observable sphere by factors we cannot measure and may never determine. The unsettling truth is not simply that the universe contains a staggering number of galaxies. It is that after more than a century of trying, after building the most powerful telescopes in human history, after staring at the sky for weeks at a time and collecting every photon that the darkness would yield, the real number is still hidden. It is hidden behind faintness, hidden behind distance, hidden behind the mergers that erased billions of early galaxies from the present-day census, hidden behind the surface brightness limits that render entire populations invisible, hidden behind definitions that shift the count by orders of magnitude, and hidden, most fundamentally, behind the edge of observation itself, the cosmic horizon beyond which the universe continues in silence, full of galaxies whose light will never reach any telescope that any civilization within our observable volume will ever build. We did not get an answer. We got something more valuable. We got a measure of how much remains unknown. And in a cosmos this vast, that measure may be the most important number of all.